Okay, so hello everyone to our next N3AS seminar, and today we are happy to have Ilaria Caiazzo. Hopefully didn't pronounce it too badly.
Close enough. It's a hard name. Caiazzo.
Who is gonna tell us about merger remnants and double phase stars, studying exotic white dwarfs with ZTF and Gaia. Please, Ilaria, go ahead.
Thank you very much. Thank you for the invitation. I'm very happy to talk about my work on exotic white dwarfs today. I have lots of collaborators. I didn't list them all because there are too many, but Caltech, UBC, Warwick, lots of people from all over the world, and all studying white dwarfs. And so white dwarfs are very common blue objects. They're the most common star corpses, as more than 95% of all stars are destined to become white dwarfs. And the most typical white dwarf, wait a second. Yes, the typical white dwarf, is the 0.6 solar masses white dwarf with the radius similar to that of the Earth. And they're usually born very, very hot. So they're very, very blue, but they're tiny, and therefore they're very faint. And again, the typical 0.6 solar masses white dwarf has a core that is made of the ashes from helium burning of the progenitor star, so mostly carbon and oxygen. And then the atmosphere of the white dwarf is stratified because heavy elements sink very fast because of the high gravity on the surface of the white dwarf, and therefore the surface of the white dwarf is usually composed by the lightest element present, and that's usually hydrogen. And so here you can see the spectrum of a typical white dwarf, where you can only see absorption line of hydrogen. In this case, it's the Balmer line because this is an optical spectrum. But there's still lots and lots of open questions about white dwarfs, and they usually revolve around atypical ones. We know the typical white dwarf pretty well now, how it evolves, where it comes from, but there's still a lot of questions about the atypical, like the very massive white dwarfs, what are they composed of? What's the maximum mass for a star to become a white dwarf? And then there's lots and lots of different atmospheric compositions. I told you about the hydrogen, that's the most common, but lots of them actually show helium because they lost the hydrogen, or they have way more complicated compositions. There's carbon dominated, polluted, etc., etc. And each one of these weird and atypical white dwarfs come with their own set of questions about their formations, their evolutions, where did they come from, etc., etc. And of course, I've done, all of the open questions would not fit in one slide or many slides, and I cannot list them all. But there's still a lot to learn about white dwarfs. They can teach us a lot about other things, other fields of astrophysics too. And one question that I like to mention that I'm very interested in are magnetic white dwarfs. So about 20% of white dwarfs happen to be magnetic. And the magnetic fields on their surfaces range from a few tens of kilogauss to ones that are almost a gigagauss, which is, more than 1 billion times the magnetic field of the Earth. And we still don't know why some white dwarfs are magnetic and some aren't, or where this huge diversity in magnetic field comes from. And there are many theories, and there's a lot of new ones are coming. So these are actually starting to be, again, a hot topic in white dwarfs community. But one of the possibility for at least the most magnetic ones is that they come from double white dwarf mergers, because when you have two white dwarfs in a binary, they can emit gravitational waves, and so they can merge, similar to neutron stars. And then if the remnant is very massive, it will explode in a type 1a supernova. But if it doesn't explode, it's low mass enough, then you'll have another white dwarf. And since you have a lot of very strong dynamos arising during the merger, the final remnant is probably going to be highly magnetized. This is a very exciting moment to study white dwarfs. There's a lot of things going on in the white dwarf community because there's a lot of new surveys, photometric and spectroscopic surveys that are giving us a lot of data and to find and study white dwarfs. And I'd like to mention first Gaia, because really Gaia has been revolutionary in a lot of fields of astrophysics and especially for white dwarfs. So Gaia is this European mission that measures distances to billions of stars. And having the distance for a white dwarf is very important because the way you identify a white dwarf is that it's a blue object, a blue and faint object. However, how faint it is, you don't know unless you have the distance. While if it could just be a blue star that is just very far away, for example. And so before Gaia, most of the white dwarfs, in order to be confirmed as a white dwarf, they needed to have a spectrum taken. While since Gaia, so this is the Gaia HR diagram, the white dwarfs can very easily be identified by residing in this lower left corner. And so from before Gaia, we had, so this is a plot of before Gaia and after Gaia. Before Gaia, we had like maybe about 35,000 white dwarfs that were mostly in the northern hemisphere because they were identified through spectroscopic surveys, SDSS mostly. And so it was very unbiased, a biased sample, and it was mostly the brightest ones. But after Gaia, this is after Gaia DR2 in 2018, we now have a much bigger sample. After the latest ones, we have about 400,000 white dwarfs, and they're uniformly distributed all over the sky, and it's much more uniform and a much deeper sample. So since Gaia, we were able to start studying white dwarfs and counting them, you know, like making volume limited samples or magnitude limited samples. And so right after the first big release of Gaia came out, there were already like lots and lots of paper studying different, just by looking at the HR diagram of white dwarfs, there were a lot of new things to discover. And in particular, this was very helpful for the more massive white dwarfs because massive white dwarfs are very rare simply because massive stars are very rare. And so since massive stars create massive white dwarfs, as you go to more and more massive white dwarfs, you find less and less white dwarfs. And they live in this part of the HR diagram. So they're usually the bluest and faintest of all the white dwarfs because they're very tiny. But, you know, since we now had a huge sample of massive white dwarfs, thanks to Gaia, we could start looking at them. And so this paper, for example, where they found out just from the HR diagram that this accumulation of object was probably due to the fact that white dwarfs crystallize around the temperature, and that's why they accumulate on the HR diagram. Again, lots and lots of discoveries. I don't have time to get through all of them, but I'd like to mention this work on massive white dwarfs from Lisa Fleury, who's a graduate student at UBC in Canada, in which she studied massive white dwarfs in Gaia. And again, here, this is the HR diagram. She picked the more massive ones that you can see. These are cooling models for white dwarfs of different masses, 0.95, etc. So she picked all of the ones above 0.95 solar masses to study. And so she used different available models for white dwarf to see how they're distributed in age and mass. And you can see that there is a big overabundance of white dwarfs between 3 and 5 gigayears ago, which could be due to two things. One could be that the models are not good enough to explain the white dwarfs, and maybe that there is a delay. And so the white dwarfs stay brighter for longer than the models predict. However, the other possibility is that in those times, 3 to 5 gigayears ago, there were more white dwarfs produced. And so that overabundance comes from that. And indeed, if you take into account the star formation rate of the galaxy, so this is a paper that came out also from Gaia, using a main sequence and evolved stars, so no white dwarfs. They found that the star formation rate was going down, 10 gigayears ago, etc., etc. But then there was a hump in the star formation rate between 5 and 2 gigayears ago, probably due to a merger with a satellite galaxy of the Milky Way. And so if you include that, then this overabundance is very well described by the star formation rate. So this is a very nice result because it just reinforces this star formation rate that was just found with the different populations, main sequence stars, but this time with white dwarfs. But from the same sample, so I don't know if some of you have read about the delays of white dwarfs. So there's also another delay, which is the Q branch, which that is 10 gigayears of delay. So this, I'm not talking about that, just in case you were curious. That's an all different story. But in this case, for this overabundance of white dwarfs, it's very nicely explained by the star formation rate. But there was also another thing that we could see from this sample when we sliced it in different mass bins. And here I'm showing the cumulative distribution of white dwarfs with age. So I'm just plotting how many white dwarfs there are below a certain age. And in orange is what's predicted by the star formation rate. And in blue is what's observed with Gaia. And you can see that in the two lowest mass bins, the agreement is very nice. The distributions agree very well. However, in the highest mass bins, above 1.1 solar masses, the observed distribution of white dwarfs is way more uniform in age. And that is something that we kind of expected, but it's very nice to see it so clearly. And that's because in these higher mass bins is where you expect the most contribution of white dwarfs that are the remnants of mergers. Because, as I told you, the higher you go in mass, the more rare the white dwarfs become. But this is the bin in which you expect a lot of mergers, because if you take the average 0.6 solar mass white dwarf, then the average merger will be above 1 solar mass, is maybe 1.1, 1.2, 1.3. And so we have a large contribution of mergers in this bin, and that's diluting the distribution in age, because the white dwarfs that come from mergers have an additional delay that comes from the evolution of the binary before the merger. And so we are not really looking at the same evolution as the single ones. So this is very nice. We know that there are a lot of mergers, especially in the more massive bins. But how do you distinguish a merger? How do you say, okay, this one in particular is a merger and not a normal white dwarfs that came from single star evolution? Well, of course, it's going to be easier to find them among the massive ones, as I just showed. But also, we expect them to be highly magnetized, as I was telling you before, because of the strong dynamos in the mergers. And something that I have not mentioned is that we expect them to be rapidly rotating, because when you have two white dwarfs that orbit each other, when they merge, some of that orbital angular momentum has to be transferred into the final remnant. And ZTF, the Zwicky Transient Facility, is a great survey to find this type of objects, and I'll tell you why. But first, let me just quickly mention what is the Zwicky Transient Facility for those who don't know. The Zwicky Transient Facility is a synoptic survey that is led by Caltech. It's at Palomar Observatory on the 48-inch telescope. And as I was saying, it's led by Caltech, but with a big collaboration of other institutions. And what it does is that it images the entire sky every couple of nights, the entire northern sky every couple of nights. And so it was designed to find transients. Of course, if you image this the sky at a high cadence, you're very likely to find, for example, new supernovae as soon as they appear in the sky. So it's been very successful at finding supernovae, TDEs, etc. But it's also an incredible variable stars facility as well. And that's because it has this huge field of view, 47 square degrees. You can see it here compared to other present or future surveys. And so you can really get very quickly hundreds and hundreds of epochs for each source in the sky. And so you can build these light curves that go on for now more than almost 5 years of almost daily cadence light curves. And so it's perfect to look for periodic variable stars, so stars that vary in luminosity periodically. And that's exactly what these mergers are doing. And that's because if you have a highly magnetized white dwarf, you expect the surface emission to be somehow inhomogeneous. You can have dark spots or hot spots or gradients in temperatures. And so if you have an inhomogeneous emission and the white dwarf is rotating, then you will see its luminosity to go up and down. Maybe the hotspot is coming in and out of the line of sight as the white dwarf rotates. So the white dwarf is photometrically variable on the period of rotation. And that's exactly how we decided to go and look for this type of white dwarfs. We took the Gaia catalog of white dwarfs, focusing mostly on the massive ones, because that's where we know that these mergers mostly are. And then we looked for periods in the ZTF data. And then once we found one, we found this white dwarf is a white dwarf, I know it from Gaia, it's periodic. We also follow them up with better photometry to make sure that the period is real. But then to really understand if this periodic white dwarf is really magnetic, we also needed to get spectra. Because of course, variability in white dwarfs can be caused by other things, pulsations, binaries, etc., etc. And so we got spectra of all of them. And I'm just gonna quickly tell you how we figure out if a white dwarf is magnetic from its spectrum. Here, I already showed you this. This is the spectrum of a normal white dwarf with the hydrogen lines. Well, if you have magnetic field in the atmosphere of the white dwarf, the energy levels of the hydrogen atom, without magnetic field, they're degenerate. But with the magnetic field, the degeneracy in M is lifted. And so you have 3 different possible transitions, delta M plus 1, delta M minus 1, or delta M equals 0. And that's exactly what you can see in the spectrum of the white dwarf. Here is, for example, for 2 megagauss or 11 megagauss. You don't see one line at a certain transition, but you see 3. And how far apart they are from each other depends on how strong the magnetic field is. So if you take a spectrum of a white dwarf, you can not only get a sense if it's magnetic or not, but you can also get a sense of the magnetic field strength on the surface of the white dwarf. Unfortunately, if you go to higher fields, it becomes more complicated than just a simple Zeeman splitting, because as you can see here in this right plot, this is where you would expect the transition of hydrogen to be at different magnetic fields in wavelength. And you can see at low energy again, the Zeeman splitting, you see 3. But then as you go to higher and higher energies, more degeneracies are lifted and you see more components, and then the components get shifted quite a lot around. And so it becomes way more complicated to find them in the spectra of white dwarf. Especially if they move around too fast. And when you're looking at the surface of a white dwarf, you don't see one magnetic field strength, but I don't know, maybe a dipole, maybe something more complicated. You're summing over the surface, so you're summing over several field strengths. Then you can wash out the absorption lines. Fortunately, some of the lines goes to a minimum or a maximum in energy at certain magnetic field strengths. And so those ones will still be strong features in the spectrum of the white dwarf. So for very high magnetic field, we try to look for those features. They're called stationary features. So close little parentheses on magnetic white dwarfs. I'll go next to the results of our search. So this was the first result, the first object that we really looked at. It stood out among the sample because it had a very short period, around 7 minutes. And I don't know if I've mentioned, normal white dwarfs have periods that go from a few, several hours to several days. So 7 minutes is extremely short. So that's a good indication that this white dwarf could be a merger remnant. Also, it was one of the bluest objects in Gaia. You can see here in the HR diagram. So we knew it would be very massive. And so it was just perfect. This might be a remnant. And so we got a spectrum, as I was telling you before, to get a sense of the magnetic field, if it was magnetic. And indeed it was. And we could see from the spectrum a magnetic field of 800 megagauss, which is one of the highest fields detected on a white dwarf. So very, very strongly magnetic. So this was really the poster child. This is the poster child of a candidate merger remnant, very fast rotating and very highly magnetized and very massive. And so we were also interested in figure out how massive, and so get a stronger constraint on the mass. So we got a UV photometry to constrain better the radius of the white dwarf. And we found that the radius of the white dwarf was extremely small. As I told you, white dwarfs have usually are the size of the Earth, the normal ones. This one is about the size of the moon, about 2,000 kilometers in radius. So very, very, very tiny. And so since the small white dwarfs are the most massive ones, the smaller a white dwarf, the more massive it is. This is probably one of the most massive, if not the most massive white dwarf that has ever been observed. It's very close to the Chandrasekhar limit. And of course, what's the actual mass really depends on the composition that you assume for the interior. Between 1.33 and 1.37 solar masses, depending on what you assume. But another very interesting thing about this white dwarf is that if you assume that the composition is what you get from carbon burning, which at these very high masses of white dwarf, we do expect them to be, to have undergone carbon burning at some point in their lives. And so to be mostly made of oxygen, neon, and magnesium and sodium, then the density in the core, it's so high that the sodium is undergoing electron capture. So the sodium nuclei are capturing electrons and transforming into neon nuclei. And this is very interesting. This is probably the only white dwarf that is like massive enough and dense enough for this to happen that we know of. And it's also a very interesting thing because in white dwarfs, what keeps the white dwarf up against gravity is electron degeneracy pressure. So if you remove electrons, what happens is that the white dwarf has to shrink for there to be enough pressure to keep up the same mass with less electrons. So as this process keeps going of electron captures, the white dwarf will keep shrinking. And so if it shrinks enough, then the density in the core would be enough for double electron capture to start on magnesium. And then that would be quite terrible for the white dwarf, because then it would get even smaller, and then it would probably collapse. Now, we do not know if this is going to happen. Right now, inside this core of the white dwarf, there isn't enough sodium for this to happen. But we know that sodium sediments, because of the high gravity, sodium sediments towards the core. It takes a few hundred millions of years, but it does. And so if enough sodium reaches the core, then the white dwarf might collapse. Which I think would be very cool. I wouldn't bet on it, also because there is the fact that the sedimentation takes a long time. But if the white dwarf freezes, so if it crystallizes before enough sodium has reached the core, then the composition is frozen and then nothing will happen. So it's possible that this white dwarf will stay white dwarf forever. But if it does collapse, then it could either explode in a supernova or become a neutron star. And this could be a different way that was ever thought of creating a neutron star from a single white dwarf, which would be very interesting. But again, this is all very speculative. So this was the first object of our search, and it was a very, very interesting one. And now in this past year, I've kept observing these objects and accumulating a very large sample of candidate mergers. We have now about 50 objects with a large range of magnetic fields and temperatures. They're all of quite mass, and most of them have periods below 30 minutes. So these are very good candidates for white dwarf mergers. And having such a sample of mergers is going to be great. So I still have to put it together and finally publish. Each one of them is so strange in its own way that it's taking me quite some time to put the sample together. But if we have a nice sample that we can really understand the characteristic, of course, we can start asking questions about what are the properties of merger remnants. Do they evolve differently? What are their distribution in masses, ages, magnetic fields? What's the delay time between the formation of the white dwarf binary progenitor and the merger? We can study their kinematics, for example. Of course, we can also try to maybe put a constraint on the merger rate in the galaxy. And then, of course, one thing that I'm very interested in is understanding the magnetic fields on this white dwarf. So we have this huge sample. We have increased the sample of hot magnetic white dwarfs by like 100%, many times. And then, so it's going to be a great sample to study magnetic white dwarfs. So this is all I wanted to say about mergers. Anna, do you have another 5 minutes, maybe?
I think, yes, you can take 5 minutes.
Okay, great. Because I have a new result that came from this search. It's probably, I'm not sure if it's a merger or what it is, but I found a new type of variable white dwarfs that are extremely exotic and extremely interesting. So this is the most striking guy, the most striking white dwarf. Again, you can see it in the HR diagram. It's pretty massive, probably around 1.2 solar masses. And this is the light curve that I got from in 5 different filters. It's very sinusoidal. The period is 15 minutes. And this is the spectrum that I got. This is the phase average spectrum, so taken over multiple periods. So it's kind of like the average of whatever the spectrum looks like. And you can see it's not obviously magnetic. I don't know if this is magnetic, but because the lines are very weak, but you can see them in red. I indicated helium lines, and in blue, hydrogen lines. So at a first glance, this white dwarf looks like a mixed hydrogen-helium atmosphere, and there are a lot of them known. Maybe, they have very tiny hydrogen content, and so you see the helium beneath. However, when we look at the white dwarf, at the actual phase resolved spectra, so I took different spectra at different phases of the rotation period, you can see, for example, that the hydrogen line they're quite strong at phase 1. At phase 0.5, they completely disappear. And if you look inside of the helium, they're quite strong at phase 0.5. And if you go to phase 1, they completely disappear. So this white dwarf is a double-phased white dwarf. So it's on one side, it's helium. And the other side, it's hydrogen. And we can see that because it's rotating. So we see one phase and then another phase and then et cetera, et cetera. And this has been like that for more than a year now. I took more spectra and period that's been stable for many, many years. So this is really a double-phased star, which is, I think, very exciting, very exotic. And so I think I'm finding more and more of these objects, none of them so extreme, like really double phase, but I'm finding more with varying strength of hydrogen and helium. So I'm thinking that this might be a class of objects, of double phased objects. And I have some possibility for what's going on here. One possibility is that, so this, helium white dwarfs kind of evolve. They don't stay the same as the white dwarf cool. There is this region of the HR diagram is a certain set of temperatures in which helium white dwarfs disappear. There are almost no helium white dwarfs known. And then they appear again. You see, these are the pink ones. There's very few known in this range. And then all of a sudden they appear afterwards. And so the reason why we think this is the case is that the hydrogen, even if there's very, 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 very tiny content of hydrogen, it can float and it can cover the entire surface, like an ocean on a mountainless planet. Even if you have very, very tiny amount, it can cover the entire surface and be optically thick. So in this range of temperatures, that's where the hydrogen just covers the surface. But when we get to about 30,000 degrees, which is where this line is, that's when the convection in the helium layer, which is right below the hydrogen, breaks into the hydrogen layer and destroys this very tiny hydrogen layer, and it dilutes it. And since there's so much more helium than hydrogen, the hydrogen kind of disappears at that point. And then when you start seeing helium white dwarfs below this line. And so maybe this might be a transitioning white dwarf, because as you can see from the star, it's really at that temperature. So it might be transitioning from being a DA, so a hydrogen white dwarf, to being a DB, so a helium white dwarf. And maybe what's causing this double phase is maybe there's some small magnetic field on its surface, that it's inhibiting convection on one side, but not on the other side, because on one side is stronger, for example. So this could be an idea. And just the last thing, another idea that Jim Fuller came about is that it might have actually a hydrogen ocean. And so we're seeing, the helium and the hydrogen. And the reason why you could have a hydrogen ocean on a white dwarf is, again, if you have some magnetic field that is stronger on one side, then you have a high magnetic pressure and therefore a low gas pressure. And therefore the hydrogen can diffuse towards this high magnetic field region and create a little pool of hydrogen on that one side, and in which case, and that's how we are seeing the two phases. Again, this is very preliminary. I mean, I'm submitting the paper today, but we couldn't think of any other explanations. But we want to put the results out there so people can start thinking about these very strange objects. But yeah, I wanted to show these also because I'm currently very excited about this Janus. And Janus is the double-faced god of Roman god of transition. So I thought it was a very appropriate name for this object. Thank you very much for your attention.
Thank you very much, Ilaria. This was very exciting, and I'm glad you got the additional 5 minutes. Yes. So do we have any questions for Ilaria? Okay, I see that Andreas has a question. Can you unmute yourself?
Yeah. Hi, Ilaria. Thanks. That's a really nice talk and great results. Really fantastic.
Good to see you again, by the way. It's been years.
Yes, it has been years. So that's right. Yeah, and I'm listening from Chile.
Ah, good.
Okay, so I was wondering about two things. One is a sort of statistical question. Your sample by design is looking for massive white dwarfs with strong magnetic fields and high rotation. I was wondering, are these three properties always connected in the sense that if you look for a random massive white dwarf, do they always have strong magnetic fields and fast rotation, and the other way around? Maybe I'll leave you with that question first.
That's a very good question, and I don't have a precise answer, unfortunately, because first of all, the way you find that a white dwarf is rotating, it's either if it has something on the surface, right, that it's making it variable, or because you can get rotation from pulsating white dwarfs. Right, but otherwise, a white dwarf is very homogeneous, the emission from the surface, and therefore it's very hard to get rotation periods from white dwarfs. You can get it also from radial velocities if they're rotating very fast, but it's not trivial. And so, of course, if you're finding a massive white dwarf that is photometrically variable, why is it photometrically variable? There's not that many pulsating massive white dwarfs, and so it's most likely it's going to be magnetic. So in that sense, it's hard to go there and say, is this because it's magnetic? Are they connected? Right? It's a bit tough and also there's also the problem of, so how many of the massive ones are magnetic? And that's what I'm trying to figure it out right now, because there's lots of selection problems, and this is what I'm working on right now, like trying to, because ZTF, the way I'm looking at and finding them is that because they show variability in ZTF, right? And so ZTF, of course, as if they have a high amplitude of variation, it's easier to find them than if they have a very tiny amplitude of variation. So it's a very let's say 1% variation, which I've seen some that vary 1%, but in order for ZTF to find them, they have to be very bright, right? If they are very faint, then ZTF can still find it, but they have to have like a 20-40% variation. So there's all of these subtle selections effects that I'm doing right now. Now I'm trying to figure out what's the selection effect in ZTF, and so to retrieve completion of this object. So I might have at least a constraint soon. So stay tuned.
Okay, my other question was more specific. In these Janus objects, do you have an upper bound on the magnetic field?
Yes. So I don't see any Zeeman splitting. So I know that the field cannot be more than maybe 1 or 2 megagauss. I mean, with Zeeman splitting, you can go down to hundreds of kilogauss or even less, but these lines are very shallow and big because it's a hot massive white dwarf. So I cannot say it's less than a gigagauss. That's kind of like the megagauss. Sorry, that's kind of the maximum field I can constrain. It would be nice to get spectropolarimetry, because that was much more sensitive to small fields, but this white dwarf is very faint because it's very far away. And so maybe if I find others like it, maybe I can get a better constraint.
Okay, thanks a lot, Ilaria.
Yes, thank you very much. And we have next question, I think from Charles Horowitz. Can you unmute yourself?
Yes, so thanks for the nice talk. You're very massive white dwarf. You talk about being metastable. Just wondering if you can say a little bit about the time scale for sodium electron capture, if that's what would make it metastable, and how might that affect how rare such an object is.
So what's making it metastable is not really a timescale of sodium electron capture, but more the timescale of sodium sedimentation. Because right now there isn't enough sodium in the core, because right now it's very young. This white dwarf is maybe 10 million years old, so it's completely mixed. And sodium sedimentation, so there is enough sodium in the core to, for enough electrons to be removed to make it unstable. And so the timescale that is important here, it's really the sodium sedimentation, which at this very high mass, it's kind of like hard. I mean, I think it's on the order of a few 100 million of years. But then there's the other important timescale is the timescale for freezing, for crystallization, right? Because that would stop the sedimentation of sodium. And so depending on which one is first, but that's also poorly constrained also because this white dwarf, it's emitting neutrinos at a higher rate than a normal white dwarf because there is electron capture on sodium. And so maybe it's cooling faster than a normal white dwarf. So there's, I would say that the timescales are pretty uncertain, but they are on the order of hundreds of millions of years.
So the core could freeze and that would protect it from electron capture and demise?
It would protect it from more sodium to get into the core and proceed with more electron capture, yes.
Thanks.
Okay, thank you very much for the question. And we have a next question from Susan Gardner. Can you unmute yourself, Susan?
Oh, yes, thank you. Thanks for the nice talk. I guess I have two very simple, possibly connected questions. One concerned the idea that, in fact, that you see an excess of white dwarfs due to a galactic merger event or impact, I guess, with a stellar disk, maybe 2 to 4 giga-years ago. And therefore, I'm thinking that some of the effects you're seeing in enhanced or discovering these interesting exotic objects might also be a consequence of that nature merger event. And so one would be very curious to know if one could assess that merger rate in a, beyond the local environment. And so I guess I'm wondering whether you agree that's actually would have impact on this exotic merger rate. And secondly, whether or not if we were to discover, I guess, study these systems in LISA, whether our discovery volume would be large enough that we'd be able to see whether or not the merger rates change beyond our immediate solar neighborhood.
Okay, so regarding the first question, the fact that a merger of the Milky Way with a satellite galaxy, I don't know what kind of influence it would have to the merger rate of white dwarfs, because
didn't you say that? I'm so sorry. I thought you said
no,
that. I
no.
you said a merger.
I'm sorry.
Due to a merger event, and therefore, please straighten me out.
Okay, I'm gonna explain again. I know I went very fast and I put a lot of stuff into this talk, so I apologize. The first part of the talk, the part about the Lisa Fleury paper that was about massive white dwarfs, all massive white dwarfs, not also merger events. There was lots of massive white dwarfs, and we could see that it was an excess of massive white dwarfs between 2 and 5 giga-years ago. And that we think, and that it's related to a bump in star formation rate around that time. And that bump in star formation rate might be caused by the merger of the Milky Way with a satellite galaxy. So I think that's what
I thought you said. And if you have more white dwarfs, then it seems
more white dwarfs,
you get merger events. Just saying.
Yeah, but the thing is, with the merger events, it takes some time for the merger to happen, which we don't really know what it is, like the merger delay, because you form the white dwarfs, right? So you form the binary. Actually, you form the binary stars. They have to become stars, and then they have to merge as 2 white dwarfs, right? So that included a delay that that's what I was talking about afterwards, what I was showing the 1.15 to 1.3 solar mass spin. That's where we have a lot of mergers, or we expect to have a lot of mergers. Those will not really trace the star formation rate, will not trace the history of the galaxy, because they have this additional delay that is probably different from system to system, depending on how wide the binary was when it was formed, and blah, blah, blah. There's a lot of things that can go in there. And there's a lot of population synthesis studies to try and figure out what is that delay. And that's actually something that maybe with this white dwarf merger remnants, we can actually constrain, because from the kinematic of the merger remnants, we can see if there is a delay, because older white dwarfs move faster on average in the galaxy. So maybe we can constrain that. Yeah, and then of course it would be super cool if with Lisa we could trace the merger rate around the galaxy, and I mean it's gonna be quite exciting to see. I don't know how good we will be doing in terms of selection defects with Lisa as well, right? Because you're looking at, but I think it's fine. I mean, current studies of double white dwarfs, there's been a lot of like white dwarfs that will be very strong in Lisa, and those have lots of selection effects. But I guess with Lisa we want, because it's just how close the two white dwarfs are together. So hopefully.
Okay, I found that super helpful. Thanks so much for explaining. Thanks for the talk.
Yeah, thank you. So we also have a question from George Fuller, or George and group at INT.
Yeah, thank you. So thanks for the great talk. That was a very, very interesting. So I'm just asking about the electron capture induced runaway. That seems very interesting to me. And this is kind of an addendum, a technical addendum to what Chuck was asking about. So I understand that it's kind of the settling of sodium that controls that runaway. You can't get the runaway until you get enough sodium. I'm just wondering, what are the central densities of these stars where they're, where the sodium settling is significant? In particular, what's the electron Fermi energy there?
So let me pull it up.
These are compact things, right? They're close to.
Yes. So the center, yes, the center of the white dwarf is above. It's above the. Sorry, let me find it. It's above the threshold for sodium from electron capture on sodium. And so the threshold that we are using in terms of density, I'm putting it up on the paper, I don't remember exactly. Where was it?
I'm guessing it's an order of a few MeV.
Yeah, so the density is about a few, around maybe 6 × 10⁹. Something like that, the density of the white dwarf.
That's maybe an electron Fermi energy at 6 or 7 MeV. So those are relativistic electrons at the top of the Fermi sea. And that's why you're close to instability there.
Yeah, exactly. So no, sorry, it's a bit. So for sodium, we used 1.7 × 10⁹ grams per centimeter cubed.
Very good. That's a few MeV.
For the threshold, and the density. It's a bit above that in the center of the white dwarf.
Yeah, very good. And so my question is this really, is there any way to get the electron capture rate accelerated? I understand that the bottleneck in this model to get to the runaway is really the settling of, as you answered Chuck's question, the settling of sodium and how that, so it's the concentration of sodium in the center that really is the bottleneck in the time scale for the runaway. I'm just wondering if there's anything else that can enhance the electron capture rate. So the temperatures in white dwarfs are, they're low in the center because it's a white dwarf. It's supported by electron degeneracy. But I'm wondering if there's some remnant of heat left over from the remnant, and it takes a while for the heat to diffuse out. So I'm just wondering what the central temperatures might be, and whether you could get kind of a tail on that electron distribution function, a tail on the nice Fermi-Dirac function that would give you some higher energy electrons. And of course, the electron capture rate will go as a very sensitive function of that extra.
Yeah, I see what you're saying. Sorry.
If I could interrupt, George, I think they're really degenerate at these very high densities. So I'm not sure temperature is the knob to play with. But if the composition is not what we think it is, there could easily be something with the lower electron capture threshold.
you're right, Chuck, and that would be a quicker route to neutralization. Absolutely, in a runaway.
Well, the fact that we see this object, it means that it cannot be too fast, right? It's still there, and if it was too fast, it would be very, very unlikely that we found one, especially because it's only 40 parsecs away. So it's very close, so it cannot be too rare.
Well, we're in the business of neutrinos here. And so, I mean, something 40 parsecs away that collapses and is a nice neutrino source would be very welcome.
Yeah, if this guy's going to go supernova at 40 parsecs.
That would be amazing. I wouldn't bet on it because, since you have, if you really have like this, additional neutrino emission, it means that it's going to cool even faster than normal white dwarfs. So it's probably going to crystallize very quickly. So if I had to bet, I would say that it won't collapse. But it would be nice if it did.
Because it's still capturing now, I assume that can you estimate what's the neutrino flux you will get out of this?
I guess you can. I did not do it. I think there's a lot of uncertainties in it.
Rough ballpark, order of magnitude, right? 40 parsecond is a very nice distance to have. I mean, 87A is 50 kiloparsecond away. Obviously, there's a lot more neutrinos from that event, but nevertheless, it buys you a lot of flux factor.
And Chuck, to your point, if there's other stuff, I mean, I think the electron capture on the ground state of sodium will go to the ground state of neon. But if there's some other stuff where you have an electron capture going to an excited state that then decays by, say, particle emission or photon decay, then that would be a way to siphon some energy off of the high electron Fermi energy and put it into thermal energy.
There's also some kind of a competition because if you have finite temperatures, then the Chandrasekhar mass somehow gets raised.
That's what I'm saying. So it actually increases a little bit because you're right. You get more pressure.
Right. But it'll be very interesting to see that what kind of a steady state, what kind of the flux you are having now. It's 40 parsecond again.
It's intriguing.
It's intriguing, yeah.
We want that thing to collapse. So
why are we doing the calculation? After we finish, it can collapse.
How rare should we think of this object? How should we think of its rareness?
Well, it's very hard to determine with one object. But the fact that it's only 40 parsecs away, it means that, it's a pretty common object. I did this calculation a long time ago. I cannot remember, how many white dwarfs there are within 50 parsecs, but it's very, you have to assume it's pretty common. Yes. It's as maybe, I have to get back to that because to you like how common this is in terms of like compared to other white dwarfs maybe, but
if this one is at 40 parsecs, why haven't you found hundreds of them or thousands of them a little further away?
Because it's so tiny. 2,000 kilometers. It's so tiny that it has to be pretty close and hot to be detected. And also, actually, this guy was just sitting around. It has been observed with STSS many years ago. It's just the reason why we took a closer look. It's because I realized that it was variable in ZTF. So there might be others out there. I mean, Kilik there was just a recent paper by Kilik, was like a few months ago about the closest massive white dwarfs, and he found other that could be as massive. I mean, this one we had a very good, you have to follow them up at least in the UV to get a good sense of the radius because they're all pretty hot. But there could be others out there. It's more of a question of we haven't been looking very hard.
So the galaxy could be crawling with 1.35 solar mass moons?
Yes. Indeed. For example, if this was I read that on my slide. So yeah, if this was, no, it's not on the slide, but if this was creating neutron stars, for example, then, this would make up maybe at least 20% of the neutron star population. So it will be a big chunk of neutron stars that come from these, just by the distance, right? Just that tells you how common these are. So yes, there's a lot of moon-sized 1.3 solar masses objects out there. It's just they're tiny, they're hard to find.
Yeah, a related question, once they become neutron stars, then they become easier to find, presumably because they're born hot again, right? Then the collapse will make them hotter, and then they'll spend another million years being visible in X-rays. Can you do forensics of that sort? Is there something special about neutron stars that you form in this channel?
Yeah, well, from just conservation, of angular momentum and magnetic field, you get a pretty standard neutron star. A few milliseconds and 10 to the 13 Gauss.
But they don't have a supernova remnant around them.
So one thing is that they would probably not move very fast.
Yeah, the kick of
because
is very little. Yeah,
you don't get a kick from the supernova. And so if this is a real population of neutron stars, that you would have it would be a very slow moving population compared to neutron star, which go very fast usually compared to normal stars.
But you get all the neutrinos from making it.
Yes.
That's all fine.
You have to convert everything into iron. So.
It's always a successful explosion. It's always a successful explosion, and it has a very low mass end because all your things are limited to definitely below 1.4, for sure before 1.4. So more like a 1.1, 1.2 solar mass-ish, the neutron star you're going to make. Maybe even smaller because part of it might be ejected.
Yeah, these are the sorts of proto-neutron stars and neutron stars that we like. We don't have to worry about the explosion mechanism.
Yeah.
But I have a question about the fact that there is no debris around the neutron star when it's born. So unlike supernova 87A, even if there was a neutron star there, we are probably not going to see it for the first 50 years or so, right?
Yeah.
There is then, if this channel is actually operating at a sizable fraction, then there is some rate at which you should see a 10-year-old neutron star.
That's true.
But we know, Sanjay, that this hasn't happened in our galaxy since 87A.
Yeah, so that puts a limit. Over some period of time, this should have been visible as a very hot neutron star in our galaxy. And, since the beginning of X-ray astronomy or something, there must be some sort of limit you can put on how often they're formed.
I haven't got into this much detail, and because it's so uncertain that this white dwarf is really gonna collapse. It's a neat idea, but it's so uncertain that I didn't want really to get into all of these calculations. I didn't put them in the paper because I don't want to really. I know you like the idea, and you're very welcome to play around with it. But again, it's very speculative, and so I think it also would be too large of a fraction of neutron stars. I haven't got into, does it make sense from the amount of neutron stars we would get versus the neutron stars that we see? I haven't got into all of these calculations because if I had to bet, I would say this will stay stable. However,
okay, so I think maybe we end the official part, and if you can stay, we can have some discussion if people are interested, but I will stop the recording now.
Okay, sounds good.